So, very good. Let's start with clearing up various things that we dealt with in a slipshod manner, or I didn't say carefully. Firstly, we know what this symbol means, right? This is the hero of our story. It's the metric, and we've used it a lot, and we'll keep using it a lot. But I've sometimes used the symbol G alpha beta, and while thinking about it, it occurs to me I didn't define it. Okay, most of you know what it means, but for those who don't, what this means is the inverse matrix of G mu nu. Think of G mu nu as a 4x4 matrix at any given point in space. As a matrix, it has an inverse. Okay, and G upper mu nu is simply the inverse matrix of G lower mu nu. What does that mean? In equations, it means that G alpha beta is defined by the equation G alpha theta G theta beta is equal to delta alpha beta. Okay. Now, because G is symmetric, its inverse is also symmetric. Okay. Also, G transforms like a tensor with lower indices. What does that mean for G inverse? It means that G inverse transforms like a tensor with upper indices. Why is that the case? This is because under a transformation, this G picks up a transformation factor of del x by del x prime. But G inverse has to transform in such a way so as to cancel that transformation, because in both frames, both in the initial frame and in the final frame, G times G inverse is delta. So the transformation has to cancel. Therefore, it has to transform by the inverse factor. And you remember that upper indices transform by the inverse factor as compared to lower indices. Was this clear? Would anyone like me to write this in equations? Somebody who does, don't feel shy. Okay, if it's not clear, you should say. Equations? No? Yes? Okay. No, delta function by definition is something that is one, but by this simple, what I mean is simple that is one of these two indices are equal. So delta 1 1 is equal to 1, delta 2 2 is equal to 1. I'm sorry. Okay, this is my definition of delta, and so it doesn't change at all. Okay, no, good question. The question is, I think maybe the question is, regard delta as a tensor with one upper index and one lower index. Then what happens when you transform it? Let's check. Okay, let's remember the rule for transformations. Okay, A mu was equal to del x mu by del x, let's call it nu prime, A nu prime. That was the rule for the transformation of an upper index. What was the rule for the transformation of a lower index? A mu was equal to del x nu prime, let's go, nu prime by del x mu A nu. Right? So now, and what was the rule for the transformation of something with both upper and lower indices? Each index transforms on its own. As far as the transformation one index goes, the other index goes along for the ride. So let's work it out now. Okay. So delta alpha beta is equal to what? This guy transforms like an upper index. So dx alpha by dx prime, let's call it alpha prime, delta alpha prime. So we've transformed the upper index. Now we have to transform the lower index. How does this transform? This transforms like, according to that rule. So we'll put a beta prime here, and we'll get a dx prime beta prime by dx beta. Now, suppose in the primed frame, this tensor was delta. I want to know what it becomes in the unprimed frame. Okay, so I know what this is. The question is to calculate this. So this is at the moment just a definition. We want to know what it is. Okay, but this is contracting indices alpha and beta. So what it does is set the beta index to the alpha index. But these two matrices, what?
Beta prime to alpha prime.
Beta prime to alpha prime, thank you. Beta prime to alpha prime. But that contracts these two indices in these two of these two objects, and these two matrices are inverses of each other. So by algebra, let's call this delta tilde, whatever it is. Okay? By algebra, this is, do you understand? And therefore, we've proved that the object delta alpha beta, regarded as an object with one index upper and one index lower, is an invariant tensor. Which means if you transform it in the new coordinate system, it takes the same form as it did in the old coordinate system. Okay, so it's an excellent question. Okay? Invariant tensors, of course, very rare. Suppose we had tried to invent the tensor delta alpha beta like this. I have a tensor which in my coordinate frame is one of the two indices are equal, and I declare that it's a lower tensor. Then if I transformed it, it would have transformed into something complicated. In fact, that's roughly what we did in the first class for defining the metric. The metric was delta, was eta, but that's almost delta. And then transforming eta, we got more complicated metrics. Okay? However, delta alpha beta, regarded with one index upper and one index lower, is an invariant tensor. Okay, excellent question. Okay, since this has come up, okay, was this part clear? Was this business about G clear? Would anyone like me to show the algebra? Okay.
So, but isn't that the consequence of your definition that you are keeping delta alpha beta is always defined as 0 or 1?
It's always defined as 0 or 1, but let's say I define it as 0 or 1 in the coordinate system x prime. Then I want to know what it becomes by using the tensor transformation rule, what it becomes in the coordinate system x. So I know what it was in the coordinate system x prime, and I know the rule for transforming it to the coordinate system x. That rule gives me something. The miracle is that it gives me the same definition in the new coordinate system. That even in the new coordinate system, if you take 1 and 1, it's 1, 1 and 0 is 0. That didn't have to be. Do you understand? Okay? This part was a definition. Transformation rule that we know. And then this was algebra. The algebra worked, but it didn't have to work. Do you understand? Excellent. More questions, comments? Excellent. So this is clear. So this object here, G with upper indices, is an object which has it's a tensor, symmetric tensor with two upper indices. Okay, and it's often a useful object. In fact, I use this object in giving you the formula for what gamma was, without even defining it, but you know what it means. Okay. Now there are various other things that we need to briefly clear up before moving on to things. Let me do them one at a time. Let's go back to the first lecture where we worked out the geodesic motion. We worked out the motion of a free particle in a curved space. If you remember, we got a formula. Which I'll quickly rederive for you because it's so easy to derive, also so that we won't make mistakes. We got a formula, and I want to now reinterpret that formula in light of our new knowledge. Okay? So I'll briefly remind you how it went. We had G alpha beta dx alpha by d lambda dx beta by d lambda. And then, we had some other term. We got E is equal to 1, which told us that dx lambda by d, that this square was 1, right? That was the equation of motion that came from varying that E guy. Okay? And then we needed to get the equation of motion for x. That we got by varying this Lagrange. There was some m, but it didn't change the equation. Okay? And in the variation, there are three places where you can vary. You can vary the x inside G, you can vary the x inside here, or you can vary the x inside here. These two give you something symmetric, so it's clearly a factor of 2. So basically there are two separate variations, the x inside here and the x inside here. The x inside here, so let's say that I vary x theta. That gives me g alpha beta comma theta. Now we're using a notation from yesterday where comma means ordinary derivative. Right? Because we took the derivative of this and then the change in delta x theta. So I'm looking at the coefficient of delta x theta. Then we have the variation of x here. In order to compute that variation, we integrate it by parts. So you get a minus sign, then d by d lambda acts on this and this. One of the terms is when d by d lambda acts here. That gives us minus 2, because the factor of 2, because of two of them, d2 by d lambda squared. Now we wanted to call this guy theta, because we're looking at the variation of x theta. So x beta g theta beta. Theta beta. Is that good? That is the variation where the d by d lambda hits here. And then we had a variation where the d by d lambda hit here. Okay? So that gives a minus 2 g theta beta dx beta by d lambda. But then we got a derivative here. So let's, why does that change as a function of lambda? It changes because x changes. So let's put a d zeta dx zeta by d lambda. Is this clear? This is the equation we got from varying this action. Okay. Just for fun, I'll divide through by 2. Well, that's the factor of. Wait, so I varied this and I varied this. Those gave equivalent things. That's the factor of 2. Okay? And then each variation has d by d lambda acting either here or there. Here?
He is talking about the dx alpha by d lambda x alpha dot and x beta dot should.
Thank you. Thank you. That's what you meant? Okay, great. Thank you. Minus. Okay, are we good now? All indices are okay, right? Okay. Now, so our equation of motion was this is equal to 0. Okay. Now, you see here what we have is the free index is this theta. So what I'm going to do is to take this whole equation and multiply it by g beta mu. So if this is 0, I can multiply it by g beta mu and it will continue to be 0. And just make it look a little more familiar. Okay? So when I do that, what does this term become? This term becomes d2 x mu by d lambda squared. Is this clear? Because I'm using that beta, when I contract, I get delta theta mu, the definition of the inverse metric. Thank you. Thank you. Thank you. Thank you. Thank you. Yes? Sorry. So is this clear? Excellent. Now, what I will get here. So this is what I have, and then I'll add the other things. So what I have here is g mu theta. Okay, you want a minus? I'll put a minus. Okay, yeah. Okay, g mu theta. I'll put this with the same sign. So, and let me put a half. Okay, let me put the half here. Okay, so I'll get a 2 d zeta g theta beta, okay, d zeta g theta beta, and then minus g, okay, now this guy has zeta and beta as these indices. So let me call this alpha and alpha. So dummy index, I can do that. So we call it alpha, beta. Here now I've got alpha and beta, so this is minus g alpha beta theta dx alpha by d lambda dx beta by d lambda. Excellent. Now one more manipulation. This is same as d2 mu by d lambda squared plus g mu theta by 2, and then I use the fact that this guy here is symmetric in alpha and beta, so I can replace this by the symmetrization in alpha and beta. Okay, so instead of 2 this, I can write del alpha g theta beta plus del beta g theta alpha minus g alpha beta theta del x alpha by del d lambda dx beta by d lambda. Right? Simple, stupid algebra. But what is this quantity? It's the Christoffel symbol. It's the gamma that we defined yesterday. Okay. So this equation is the same as d2x mu by d lambda squared plus gamma mu alpha beta dx alpha by d lambda dx beta by d lambda is equal to 0. What does this equation mean? You see, what this equation, the way you can think of this equation is this. Let's define dx mu by d lambda is equal to u mu. U mu is the forward velocity of our particle. It is clearly the natural definition of u mu. In special relativity, we define u mu as dx mu by d proper time. What is proper time? Proper time is the coordinate such that the invariant length along proper time is -1. But this lambda coordinate has that same property. That's what this equation is saying. So lambda is the proper time along your path. So dx mu by d lambda is the forward velocity. It's the change in x mu with respect to proper time along the world line. Okay, so this is the equation d by d lambda of u mu plus gamma mu alpha beta u alpha u beta is equal to 0. Okay, now we can think of this in this way. D by d lambda, suppose we've got a trajectory. We've got the particle here and it moves here. The change in u mu as we move over distance lambda, we can think of this as u dot d on u mu is equal to 0. Okay, let's see why these two things are the same. What we've got is a trajectory that is moving like this. And I want to see how much the velocity has changed as we move a little bit along the trajectory. Okay, So how much am I moving along the trajectory? Let's say I move a distance delta lambda along this trajectory. Okay? In that time, how much have I moved in x mu? I've moved by u mu delta lambda. So if I move by delta lambda, then delta x mu is equal to u mu delta lambda. Okay? So the change in velocity is just the change in velocity we move by lambda, but we're not going to take the ordinary derivative change. We're going to take the covariant derivative change. Okay? So we're going to add this gamma here, but dotted with how far you moved, the parallel transport. We're taking into account the parallel transport as you move along this trajectory. Parallel transport by how much? By the amount you moved along the trajectory. Okay? So this equation here is keeping track of the covariant acceleration of the particle. Let me say this again. What is in ordinary special relativity, what's the acceleration? You take the velocity at one time, let's say one proper time, the velocity at another proper time, subtract the two, divide by delta lambda. That's your acceleration. Okay? This is what we want to do here, except that procedure makes no sense. Because the velocity at one time is a vector in the tangent vector space of that point on the manifold. The velocity at another point is a vector in the tangent vector space at another point of the manifold. So in order to do the subtraction, you need to first parallel transport the velocity at the first time to the velocity at the second time, and then do the subtraction. But that parallel transporting is basically achieved by replacing the ordinary derivative by the covariant derivative. That's exactly what this is doing. Is this clear? Okay? So this is the covariant version of the statement that the acceleration of a particle, of a free particle, vanishes. Okay? So the equation of motion we got by minimizing our geodesic equation, by minimizing our minimizing the length of the particle, is essentially the statement that is a covariantized version of the statement that the acceleration of a particle vanishes. So particles that move according to this minimizing distance equation move as best they can in the way that they can with locally not accelerating. Let me make that statement more precise. You see, how does this statement here differ from the statement that d by d lambda of u mu is equal to 0? It differs by this term. But we've already seen, and you will show in your exercise, that there is always a coordinate system in which gamma vanishes. In that coordinate system, what happens to this equation? It just becomes d u mu by d lambda is equal to 0. So this coordinate system at any point in which gamma vanishes is a coordinate system in which at least the laws of free motion of classical mechanics are the same as the laws in special relativity. Is this clear? However, all of general relativity is not all of special relativity, because while you can always find a coordinate system in which gamma vanishes at a point, you cannot in general find a coordinate system in which gamma vanishes at all points. So, to look at a little bit of the trajectory, for any little bit of the trajectory looks as if it's moving in special relativity in an appropriate coordinate system. However, you have to keep changing coordinate systems in order for that to be true. And so in any given coordinate system, you will see deviations from the law. That's what this is capturing. Okay? The fact that you can always find a coordinate system in which the equations of motion become those of special relativity, is called, is part of the content of this famous principle of equivalence. The statement that in a little local patch, you can always move to a coordinate system such that the equations look like those of special relativity. This is a more precise version of that statement because it tells you how local. It tells you as far as first derivatives go, this is true. It's not true for second derivatives. Well, first derivatives of velocity. It's not true for second derivatives of velocity. Okay? So basically the fact that you can get rid of gamma at any given point is a mathematical realization of this principle, which we'll keep understanding better and better as we go. Okay? Great. Please.
So in the first class you choose this E equals 1 gauge,
yes.
And then we identify this lambda with the proper time.
Yes.
So if we were to use the same formalism, what happens in case of null trajectories, because there's no proper time there?
Excellent question. Okay, in the first class, actually this formalism is easily adapted to the null case. Let me explain that. In the first class, I chose a distribution of m's which I would have to change. So I'm going to at least schematically explain this here. You remember we started out with the metric g mu nu dx mu by d lambda dx nu by d lambda d lambda. This was our action. There's a minus sign, there's a minus sign, something like that. Okay. Then what I did was to say that this was equivalent, if I believe, if I got this right, to some dx mu by d lambda dx nu by d lambda by 2. There's an e and a minus e g mu nu. Can somebody help me get the signs right? What are the signs? Minus and a plus. Excellent. Now, there is something else I could have done here. This was very convenient for what we want to discuss because setting E is equal to 1. Setting E is equal to 1 is equivalent to working with actual property. But there's another choice I could have made. And that other choice is to set E is equal to M. Okay? It was completely up to me, right? E is equal to any constant tells us that the coordinate lambda is proportional to property. E is equal to M is just scaling out, stretching out that constant. Now, if M is any non-zero value, it doesn't matter. The great thing about this is that it allows a smooth M goes to 0 limit. Okay? It allows a smooth M goes to 0 limit because now if I said M goes to 0, what does the action become? It just becomes d mu nu dx mu by d lambda dx mu by d lambda. And this term, which is just M, just drops out. Okay? So this continues to be true. And the equation that E was equal to M when you said M equals 0 tells you you've got a null geodesic. Okay? Yeah. Okay, great. Excellent. Other questions or comments? Please.
That is the u dot d u.
Yes.
That is the covariant acceleration in the direction of velocity.
Of the velocity.
So in the other direction there might be...
No, it doesn't even make sense. You see, we've got a trajectory. So the particle velocity is defined only on the trajectory. So if you want to ask what does it mean, what is the change in velocity of the trajectory, that question makes no sense. Do you understand? Let me say this again. So far when we talked about covariant derivatives, we were acting on fields. Fields are defined all over space-time. So you can take the covariant derivative in any direction. What's a derivative? It's this minus this. On the other hand, a velocity is only defined on the trajectory. So if you take the covariant derivative of the velocity in this direction, it's neither good nor bad, it's just meaningless. Do you understand? Because it's velocity here minus velocity here, but the velocity here means nothing. Velocity is only defined on this trajectory.
See, we project it onto the trajectory.
Onto the trajectory, because that's this is the only covariant derivative of velocity that makes, that is meaningful. Is this clear? There's another way. If you okay, but anything else will be confusing. You don't look satisfied. Keep talking till you're satisfied.
So just like in the circular motion,
Yes.
we say that the tangential velocity is constant, so acceleration
Yes.
is zero. But there is some acceleration in this direction.
Absolutely right. We've said nothing about the components of the velocity. These components are free. That is what you're talking about, right? Tangential, radial, so on. But even in circular motion, when we say d by dt of velocity, we mean velocity at one time minus velocity at the next, along where the particle is going, right? See, there are two things. When we normally in classical mechanics talk about a derivative of velocity, we mean with respect to time. In general relativity, we mean with respect to parameter. But that parameter is a parameter along the world line of the particle. Is this clear? On the other hand, covariant derivatives are defined for fields. Fields are defined all over space-time. So covariant derivatives can be taken in any direction. However, particle velocities can only be differentiated along the world line. So these are two different concepts. However, there's one direction in which the covariant derivative of the velocity makes sense. That's the direction that happens to point along the world line. Is this clear? Okay, it's a very good question. It's a potential confusion. Okay, so this is a confusing way of writing it, because we're pretending this is a field when it's not. Okay, but then we don't make any mistakes because we're only differentiating it along the one direction where it makes sense. You could imagine some u mu of x field, which is u mu along the trajectory and anything else outside. This is completely defined by its value in the trajectory. Anything else depends on your convention or how you continue this u mu off the world. Is this clear? Excellent question. Please. Go on, go on. You give E some dimension. I mean, yeah. Hello. Yeah. Is this still working? Okay, hopefully. Okay. Okay. Excellent. Other questions or comments? Great. So let's move on. Fine. There's one more thing that I wanted to make connection with, the first class. The first class was an attempt to do things a bit intuitively. Now we've got to act together and we're doing things a little better. And we must make clear that every intuitive thing we said in our first class matches up with a more clean treatment. In the first class, I did something. I don't know if you remember, but we talked about the Maxwell equations. We talked about how we can define A alpha in any coordinate system. And then we talked about defining F alpha beta as equal to del alpha A beta minus del beta A alpha. And we explained that this definition gave us a tensor. That if A was a tensor, F was a tensor. Now, some of you should be a bit worried about that. It sounds like it contradicts what we discussed in the previous class. In the previous class, we discussed that the derivative was not a tensor when acting on objects with indices. Okay? We had to be more sophisticated in order to define a tensorial derivative. Now, doesn't it mean that we made a mistake in our first class? How did we manage to get a tensor using just the ordinary derivative? Let's check that out. Okay? So, since you guys are now so sophisticated, you know all about differential geometry, you'd say, well, if you want to make a field strength, I know how to do it. You'd say, what I need to do is to define F alpha beta as equal to d alpha A beta minus d beta A alpha. this is right, this is wrong. Okay, but you know, we checked something in the first class. I did it on the board, you guys checked me. How could we have made such a mistake? So let's check. Okay, this guy here, what is it? This is del alpha a beta minus gamma alpha beta theta a theta. Definitely different from del alpha a beta. Okay, but what about del beta a alpha? This term, so let's put minus del beta a alpha minus gamma beta alpha alpha beta theta a theta. And that's the thing. This, as you said, this is different from this. This is different from this. But the two differences cancel each other because of the symmetry of gamma. Okay? So it's a general rule, one that you can easily verify using the same algebra, that if you've got an object with all indices down and all indices antisymmetric, alpha 1 to alpha n, okay, and you take an antisymmetric derivative, a completely antisymmetric derivative, d alpha, such that you completely antisymmetrize this object. Okay, so it's this minus n such terms, n plus 1 such terms, totally n plus 1 such terms, to completely antisymmetrize this object. Okay, this thing completely antisymmetrized. Okay, that in this all gammas cancel. Okay, and just so that you know, and maybe we will use it later on, but this operation, the object with all indices down is called an n form. All indices down and completely antisymmetric is called an n form. And there's this operation from going from an n form to an n plus 1 form by taking a completely antisymmetric derivative. That operation has a name, it's called d, called the exterior derivative. Okay, and it's a great fact about the appropriate branch of mathematics, whatever it's called, that this d operation can be defined without a metric. So this d operation is a covariant definition that makes no use of the metric. What does that mean? It means that it does not involve the Christoffel symbols. Okay, so for this very particular case, for taking completely antisymmetric derivatives of a completely antisymmetric lower index object, you can get away by using ordinary derivatives. All gammas cancel, as we've seen in an example here.
So again, we have a torsion-free connection. That's one of the
That's
requirements.
that's a requirement. That's right. Okay, so that's another clearing up thing that I wanted to do. And now finally, let's do a few more a few more small things before we move on to the main topic of today's lecture, namely to understand curvatures. Okay. Something else that I wanted to define was the tensor epsilon. I want to define a tensor. You know, at the beginning of today's class, we defined an invariant tensor, a tensor whose form was the same in every coordinate system. This was a very useful invariant tensor, delta V. There is another invariant tensor that's also very useful, and that's related to the thing that you normally call epsilon. So to start off, let's define epsilon as follows. Let epsilon be the object whose components are all 1 or minus 1, depending on some order. So let's say epsilon 0, 1, 2, 3 is 1, and then any transposition takes 1 to minus 1. Okay? Let's start off with that definition and check whether it transforms as a tensor. Okay? So let's see. So suppose I started off with that epsilon in my coordinate system, and then I transform it. What do I get? Well, I get epsilon mu1 to mu4 is equal to whatever this epsilon tilde is in the new coordinate system. Nu1 to nu4 dx prime dx prime mu 1 by dx mu 1 dx prime mu 4 by dx mu 4. Okay. Okay, so now since I've written the transformation rule this way, let's do the other way. Suppose I started off with some epsilon tilde, such that this was 1 or minus 1 in the prime coordinate system. Say this was the, and let's call this epsilon tilde. I want to find what this epsilon tilde is. Is this clear? Well, what is this? Can somebody look at this and tell me what it is? It looks like a determinant. Of which matrix? Of this Jacobian matrix, dx prime. So this is equal to epsilon mu 1 to mu 4 times determinant of dx prime by dx. You understand what I mean by dx prime by dx, right? It's a 4 cross 4 matrix whose indices are up and down. This is clear, right? This all of you know from the theory of determinants. Now this is not too bad. Why is it not too bad? It's not too bad because we've got something proportional to what we started out with. We haven't completely molded the structure, but the proportionality constant wasn't 1. Not too bad, but not that great either. Can we now make a tensor such that it really remains invariant, not up to proportionality? Well, you can. Let us remind ourselves, we sort of briefly discussed this in the first class, but I'll remind you. Suppose we have G alpha beta. Okay? The G alpha beta was equal to G prime alpha prime beta prime dx prime alpha prime by dx alpha dx prime beta prime by dx beta. You remember this? This is the rule for the transformation of the metric. Okay. So let's look at what happens to the determinant of G. Det G is equal to what? Times where we've used the rule that the product, a determinant of a product of matrices, the product of determinants of matrices. Okay, so because of our signature, the determinant is always going to be negative. So I define, suppose I define square root minus G. G is the determinant. Okay, it's a det G. The notation is, we call it G. Suppose we define square root minus G. Okay, then square root minus G is equal to square root minus G prime times det of del x prime by del x. Okay. So now let's look at the object. That is square root G times epsilon mu 1 to mu prime, mu 4. This object remains invariant, genuinely invariant under coordinate transformations. Yes? Minus 2. Thank you. Okay? How it's basically that this factor here cancels this factor here. and you have to keep your wits about you to see whether it goes up or down. Shall we go through this? Can you see it? Okay, it's so we take the transformation here, we put in the transformation from here, and that cancels. Here there was a g prime. If you want, here we would have had a square root minus g. So if we did this exercise here, we would have started with square root minus g prime. Okay, and a square root. Now that would have. See, I've shown you how g transforms. G prime transforms with the inverse. That inverse exactly cancels this. Okay, so you get back square root minus g times epsilon. Okay, this is an interesting tensor. Exercise. Check that epsilon mu1 to mu4 by square root minus g in the denominator is also an invariant tensor. What does that mean? This is a tensor such that whose values are 1 or minus 1 divided by square root g, but regarded as an upper tensor. Okay? Check that this is also an invariant tensor. Exercise. Check. So suppose I call this tensor T mu1 mu4. Let's call it upper u. Let's call this lower mu1 to mu4. Exercise. Check that T mu1 to mu4 is equal to G mu1 mu1, G mu2 mu2, G mu4 and mu4, L mu1 to mu4. Oh, T, U. What that says, we will soon get used to thinking of tensors that are related by indices being raised or lowered by powers of the metric as not different tensors, just different representations of the same thing. So this and this are not different tensors, just the index raising of this tensor. Can somebody do the second exercise in their head right now? It's an obvious thing. The signs are sometimes a bit tricky. I may have even got a sign right, plus minus. We'll have to define this. The orientation of this and the orientation of this will have to be defined to make this work. So up to some plus minus. No? Okay, fine. You leave it for you. You do it when you do your exercises. Okay, great. This is the second invariant tensor that's very, very useful. This tensor has a name. This tensor and its raised form have a name. It's sometimes called the volume form. Okay. Notice that we discussed at the beginning of the class. We discussed the following. We discussed tensors with all indices lower and antisymmetric. This is one such tensor. We've checked that it's an invariant tensor, it's got all indices lower, so on. Notice though that it has as many indices as there are indices in spacetime. Okay? Because an object with antisymmetric indices cannot have more indices than the number of dimensions of spacetime. Why not? Because two indices would have to repeat, and if it's antisymmetric, if you repeat, you get 0. Okay? This is the largest number of indices for an antisymmetric tensor to have. D is the largest number of indices an antisymmetric tensor in D dimensions can have. I told you that objects with antisymmetric indices, lower indices, are called forms. This is in 4 dimensions is a 4-dimensional form. In D dimensions would be a D-dimensional form, sometimes called a top form. The highest number of indices a form can have, and this is very special. Well, was a very interesting top form. It's an invariant top form. In fact, all top forms are proportional to this because there's only one independent component in a top form because everything's antisymmetric. Okay, this thing's called the volume form. Just one quick aside. Mathematicians, when they integrate over manifolds, integrate forms over manifolds. Maybe we'll leave this. We'll leave this form. Let me just say it. I won't try to explain it. Mathematicians, when they integrate over manifolds, integrate forms over manifolds. And this is the form that they like to integrate to get the volume of a space-time. We would say it as the volume. By the way, this we'd already seen in the first class that this was an invariant volume element. Here we saw that, right? That's actually the same as this statement in some language, but we won't get to that. Okay. Two, three quick other clearing up operations, apart from questions or comments. Questions, comments? Excellent. There are 2, 3 small little algebraic things that we need to talk about before we move on to what's really important. One thing that is very useful is the following. There is okay. Suppose I wanted to compute d mu of a mu mu1 to mu n. Where A is an object with upper indices completely antisymmetrized. Okay. So special case of this.
The first one is it's contracted with mu.
It's contracted with mu. So it's like a divergence. Okay. A special case of this is just d mu a mu, where n is 1. Okay, the divergence of a vector field. But everything I'm saying generalizes very nicely to divergences of any object that's completely antisymmetric with upper indices. Okay? I want to explain to you that there is a nice formula. There is a nicer than usual formula for this object. That's useful because, it's useful to, usually when you think in terms of gammas, you freeze. Because gamma is some complicated thing in terms of the metric. When there's some nicer than usual formula, you can think more clearly. So let's work out that nicer than usual formula. This will also give us practice in manipulating these covariant derivatives. So what does this mean? By definition, this means d mu a mu mu1 to mu n minus 1 plus how many gamma terms? N gamma terms. One of these gamma terms is special because it acts on the index that's contracting with the derivative. All the other gamma terms are the same basically because of the antisymmetry. Let's look at one of the other gamma terms, not the special one to start with. Okay, one of the other gamma terms is what? So that is plus, let's say I do with mu1, gamma mu1 alpha, which is the dummy index, mu a mu alpha, and then everything else remains unchanged, mu2 to mu n minus. Is this clear? Can you see? No, plus, because with upper indices is plus, lower indices minus. The rule for the covariant, rule for parallel transport involved a minus with upper indices, but you subtract out the parallel transported thing, so it becomes plus. Okay? Can you see that this? Yes. But first, can you see that this is what you get when you add, when the gamma is acting on the symbol mu1? Is this clear? Clear to everyone? Anyone for whom it's not clear, please speak. Okay. This is 0 because this is symmetric and this is antisymmetric. Okay. So all of the actions of gamma on any of the indices, all of the covariant action on any index apart from this mu is trivial. There's nothing special about mu1. We could do mu2, mu3. Okay? So all that's left of the gammas is when it acts on the special mu index. In that case, what do we get? In that case, we get gamma, so plus gamma mu alpha a alpha mu1 to mu n minus 1. Is this clear? If it's not clear, please speak. Is it clear, everyone? Excellent. If you don't say it's not clear, there's nothing I can do about it. Okay? There's no harm, no shame in it not being clear. So you should speak if it's not clear. Okay?
One more time, please.
One more time, yes. Let us remember how covariant derivatives act on any upper index. The rule was, let's remember with a single index. If there's an alpha, let's call it a mu1 here, and any other indices, and you want d alpha, that is equal to del alpha a mu1 and any other indices plus gamma, then the alpha goes here, this index goes. Then we get another index here which is going to be contracted with what was here, beta, these remain unchanged, and then this index goes into mu here. Are you understanding what I'm saying? That the action of these Christoffel symbols is very simple. The index that was here goes to the top of the Christoffel symbol. The index that it's replaced by a dummy index which is contracted at something at the bottom of the Christoffel symbol. And the derivative index also appears at the bottom of the Christoffel symbol. Is this clear? That's the rule for the covariant derivative. That's the rule we wrote down last time. Now I'm just applying that rule to this situation. The index that was here goes to the top of the Christoffel symbol. There was a mu here, so there's mu on top. Whatever was here is replaced by a dummy index that is contracted with what's here. And the derivative index goes here, but the derivative index was also mu. So mu mu alpha. Is this clear? Excellent. Okay? So, okay, good. So we've got a pretty simple formula for this. This divergence del mu, d mu a mu mu1 to mu n is equal to d mu a mu mu1 to mu n plus gamma mu mu alpha a alpha mu1 to mu n. Now let's see what we can say about gamma mu mu alpha. Remember the formula for gamma alpha? Okay, gamma beta mu alpha. Let's remember the formula for this. This we saw in the last class was g beta theta by 2 g mu theta alpha plus g alpha theta mu minus g mu alpha theta. Is this clear? You know, there are very few formulas in physics that one tends to remember by heart. Most things one derives as you go along. This is one of those formulas. Sorry. This is one of the formulas. This is a useful formula to remember. Okay, this is something you just keep in mind because you read it often if you're going to be using general relativity. Okay? Great. Also in the attempt to, you just look at it enough, you'll remember it. It's a very simple formula. It's just derivatives of the metric. Okay. Now, what we're interested in is not the most general case, but beta equals mu. So let's substitute. Beta is mu. That's it. Beta is mu. Okay? Now let's see. What do we have here? This guy is special, and we'll deal with it in just a minute. But let's look at this guy and this guy. Okay? This involves two dummy indices contracted like this. This also involves two dummy indices contracted like this. G mu alpha is G alpha mu. So this contraction cancels this contraction. Can you see? Is this clear? These are simply the same terms. Let me repeat it. Let me say it in formulas and then I'll say it. Well, this I'll just write out. This is G mu theta, G alpha theta mu by 2. That's what this was. And this was G minus G mu theta, G mu alpha theta by 2. These look different, but remember we've got dummy indices. The only non-dummy index here is alpha. Okay? So, let me flip the dummy indices alpha and theta. Let's flip the dummy indices mu and theta. I'll flip in this term. So every time I see a mu, I'll make it theta. Every time I see a theta, I make it mu. And here I should also be doing the flipping, but it makes no difference because G is symmetric. Okay? Now do you see, again using the symmetry of G, do you see that this term and this term are just the same? Is this clear? Okay? So these two terms just cancel out. So this is simply equal to G mu theta alpha by 2. Now, this quantity here has a nice simple simple interpretation. And to explain that to you, I need to remind you about determinants. Okay. Do you know this formula? That the formula for the variation of the metric, of the determinant of a matrix in terms of the variation of the elements of the matrix. Okay? I'm going to write down the formula and then you tell me if you I'm assuming symmetry here, otherwise there's some. Are you any familiarity here with this formula? People know this formula or not? No. Okay, let me explain it. Yeah. Give me a minute to say it the best possible. Okay. See, as you know, okay. Suppose I've got a matrix here. Okay, I've got some particular element. I'm going to choose this to be top right just so that it's easier to draw. Top left, so it's easier to draw, but Same is true of everything. Okay. As you know, you can think of the determinant of the matrix as the product of this element times the subdeterminant here, plus the product of this element times some other subdeterminant and so on. Okay? So suppose I vary this determinant. The variation, because I vary this element, what's the coefficient going to be? It's this subdeterminant. Right? This subdeterminant, sometimes called a name, it's called the minor of the element ij. Okay, it probably has a symbol also. Okay, so the variation with respect to aij is delta aij times the minor for, I'm going to call it minor, mij. Okay, that's delta g. Now, so clearly, this is the variation because of the ijth element. There's a similar, sum over everything. Okay. However, there is a well-known formula for the inverse in terms of these minors. Okay, and that well-known formula comes about from the fact that if you take aij and you multiply by mij, you get almost delta ij, but up to a factor of the determinant. So the inverse, A inverse, up to some transposition, which I'm not keeping track of, so everything I'm saying is correct for symmetric matrices, is equal to mij divided by det m. Det A. Yes?
That summation over ij's, should both the indices run from 0 to 3?
Runs from all indices, yes.
Because usually we just do one row.
But it doesn't matter. You see, what we're doing is looking at the variation with respect to any given element. So suppose I vary this element. The coefficient of that variation is clearly this. And that is true for every element. It's like this. It's like this. Suppose I have the object x1, x2, x3. That's just one object. But if I look at the variation, there are three variations. Right? There's delta x1 times x2, x3, plus delta x2 times x1, x3. So that's, you see, all you have to focus on is finding the coefficient of the variation of one element. And then there's nothing special about that element. How much does the matrix change? You see, there are n squared different independent elements. Determinant is a function of n squared variables. I want to know how much the determinant changes if I change a11 and leave all others fixed. Once I've done that, I've done my job, because then I sum over everything else. You understand? Because that's partial derivative of the determinant with respect to a11, holding all others fixed. And then you use the chain rule to get the full variation. Okay? All I'm doing here is computing that partial variation. But I know that the full dependence of the determinant on this first element is this times this. However you calculate, you could calculate it by this rule or by this rule. It doesn't matter. The dependence on this element is this. Okay? So all I've done is compute this partial derivative and then summed using the chain rule. Is this clear? Okay? So if you put this formula, substitute m is equal to det A times A inverse, you get that formula. This, by the way, is a very useful formula. You can prove it in, you can prove it in many different ways. As an exercise, let me give you an exercise. This you should know. This formula, it's a lacuna of your mathematical physics courses if you haven't been taught this. Okay, this formula, let me give you an exercise. Prove this formula by diagonalizing the matrix J. Suppose you've got a symmetric matrix and always be diagonalized. Okay? Prove the formula by diagonalization. There's 20 different, it's an elementary formula. There are many ways of proving it. I just gave you a quick explanation. Yeah.
So one problem with the notation that you use G inverse for the inverse metric, but you were using G for.
Thank you. Okay. So why did we have this diversion? We have this diversion because I wanted to explain what this could be written in terms. Now, you see, this here is the same as this here if you interpret delta as change because of the small variation of alpha. So you see that this quantity here is the same as del alpha of g by 2.
There's a factor of g here. Del alpha g over 2g.
Over 2g. Thank you. Yes. Over 2g. Which is the same as del.
Half log g.
Exactly.
Half del alpha.
Wait, I wanted a square root. Sorry, have I messed up somewhere?
Log of root g.
Log of root g. Right. So, right. So del, the way I want to write it is 1 by square root g del alpha. Minus sign here, minus signs. Minus, put a minus, probably makes difference. Okay. Good. Okay. Now, I'm putting this formula together with this formula to get this formula. D mu A mu mu1 to mu n is equal to 1 by square root of minus g d mu square root of minus g a mu1 to mu n. Is this clear? Okay? Because the term where this mu goes through the square root g cancel, we get the first term. Where it acts on this thing, you get the second term. Okay. Now, just as an illustration of how this is useful, let's use this to compute the formula for del square in curve space. Okay, we're going much slower than I'd hoped, but I had planned to discuss curvatures today. We'll hardly get that. But anyway, it's okay. Let's look at the formula for del square. So what is del square? Del square in flat space we know. It was d mu, d mu. What must it become in curved space? If we want it to be a tensor. Del mu, right? So del square, which by definition is d mu, let's call it d mu. Covariant derivatives. Now this del square is an interesting object and it acts differently on different objects. You act del square on a tensor, its action is quite complicated because each of these dels acts on all of the indices of the tensor. But let's start with baby steps. Let's look at the action on a scalar. First question, what do we get when we act d mu, covariant derivative on a scalar? Normal derivative, because it has no indices on which the gamma can act. Right? So this is d mu of a mu, some vector a mu. What is the vector a mu? A mu is equal to del mu phi. What does a derivative with an upper index mean? It means derivative raised with the inverse metric. Okay? Then we use this lovely formula which has 1 square root minus g d mu square root minus g a mu, so that was del mu phi. And if you don't like derivatives with upper indices, because derivatives are naturally lower index objects, classic lower index object, we can make it more explicit. We can write it as by minus g d mu square root g mu alpha del alpha. So the formula for del squared acting on a scalar is this formula. Okay? As a little exercise, just to make connection with things you already know, let me use this formula to find the formula for del squared in polar coordinates. You see, now going back to the first lecture, we've retreated from the lofty heights of trying to find new physics to the mundane game of trying to view old physics in new coordinates. I'm going to work in flat space, but use polar coordinates and find del squared. All of you remember that when you were undergraduates, you went through this exercise. Some very painful way, right? Okay. Okay. This is the good general framework for understanding that. So let's, all of you know the answer. Let's see if it comes out from this way of thinking. So in polar coordinates, let's say in 3 spatial dimensions. In polar coordinates, in 3 spatial dimensions, what is the metric? The metric, spatial metric, dr squared plus r squared d omega squared. Omega squared is the unit metric on the 2 sphere. D theta squared plus sine squared theta d phi squared. I won't even bother to write it. Okay? Okay, let's write it. Let's be totally explicit. So r squared d theta squared plus sine squared theta d phi squared. Okay. Now, computing gammas, even in this simple thing, is a bit of a pain. But square root g, someone wants to volunteer to calculate square root g for me. What is the metric? Let's write down the metric as a matrix. 1 r squared sine squared theta. Oh, you've got a diagonal matrix. We can calculate its determinant, right? We can do that. Okay, so what's the determinant? R to the 4 sine squared theta. What is the square root of the determinant? R squared sine theta. So g is equal to r squared sine theta. Root g. Okay, here there's no minus sign because it's a Euclidean rather than Minkowskian metric. Okay? So now let me compute very explicitly what del square is. Del square is 1 by r squared sine theta. Well, but mu is r theta of I, so let's do really explicit. Del by del r. Then here we had a GRR, upper, but that's 1, times r squared sine theta del by del r of phi. No, let's not call it phi. Phi. Phi is another coordinate. Okay. That is the component, contribution from r. Plus 1 by r squared sine theta del by del theta. Now there are 2 things that should come in here. A g theta theta and square root g. Square root g is what it was. R squared sine theta. What's g theta theta upper? G theta theta upper. 1 by r squared. It's the inverse of this matrix. Inverses usually are hard to calculate, not for diagonal matrices. Just invert the elements. Okay. By r squared. Del by del theta of psi. And then plus 1 by r squared sine squared theta. Sine theta. Del by del phi. Okay, what should I put here? R squared sine theta, that's a universal factor, times 1 by r squared sine squared theta. Okay, 1 by r squared sine squared theta. Okay, times d by d phi. Okay, now let's simplify this. in this term, the sine theta comes out because del by del r does an act on it and cancels this. So we get 1 by r squared del by del r squared del by del r psi. Plus, what about here? All factors of r come out, just an overall 1 by r squared del by del r, del by del theta, so 1 by r squared sine theta del by del theta sine theta del by del theta of psi. Now what about the last term? Everything comes out, so it's just 1 by r squared sine squared theta. And if you go and open Jackson or Griffiths or wherever you learned this formula from, if we've not messed up, you'll find I don't remember it, but you'll find that it's the right formula. Because this is not a formula you ever remember. Because all you remember is that formula, the square root g, and then work it out. It's 2 minutes. You won't make a mistake. Okay? So, so this is a bonus. In addition to understanding the deep nature of the cosmology and black holes and so on, we also get to do Jackson better. Because we understand the good mathematics of dealing with funny coordinate systems. Okay? There is one other thing I wanted to tell you about. I wanted to tell you about Lie derivatives. And anyway, since we won't have the time to really talk, let me do that. Because my plan for today's lecture was to tell you about curvatures and really head towards Einstein's equation. But it's a bad time to start talking about it 5 minutes before the end of the class. Sorry, I keep talking. Okay, so okay. Okay, let me tell you about this thing called a Lie derivative. Okay, which is often a useful idea, often a useful notion when studying. Okay, so this, up to let's say the end of the next lecture, we're largely doing the mathematics of curved spaces. Usually mathematics lectures are quite boring in a physics context, but somehow I don't feel that about these. I think this is quite fun. I hope you agree. It's just because space is such an intrinsic thing, I think even the mathematics of space is quite fun. Okay, but okay, so let me tell you about this other kind of derivative that we will have occasion to use as we move along, called a Lie derivative. Or should I just postpone that? Okay, let me. Okay, I'll postpone this. No, let me tell you. Let me tell you about it. Okay. So what's a Lie derivative? You see, I've told you about coordinate changes. Okay, you go from x mu to x prime. Now, we've talked about general coordinate changes, but it's sometimes useful to consider an infinitesimal coordinate change. So suppose you have x mu is equal to x prime mu plus epsilon, it's a small number, times f mu of x prime mu. The most general coordinate change is x mu is an arbitrary function of x prime. But if it's going to be a small coordinate change, then it is x prime plus something small. That's the coefficient of we're only going to work to linear order in this epsilon. That's what I mean by small. The coefficient of this is an arbitrary function of x prime. But we'll work only to linear order in epsilon. Okay. Now, given a field in space-time, it is sometimes useful to ask the following question. When does that field, how does that field change when you make this coordinate transformation? So let's work out the answer to this question first for a scalar field. suppose I have phi of x mu. Okay? So this becomes phi, it becomes a new function of the variables x prime. What is that new function? I'll go back to being a mathematician. I'll call it phi tilde. And phi tilde is equal to phi tilde of x prime, which is phi of x mu plus f mu of x prime with an epsilon. Now what is the change in phi? So now what is, let's work this out by Taylor expansion. So this is equal to phi of x mu plus epsilon times del mu, okay, times del mu epsilon f mu x prime times del mu of phi. Now, this f mu is slightly cumbersome notation. What it represents is the change in the coordinate x. I'm going to call this delta x. Will you permit me to call epsilon f mu? I'll make the notation delta x mu. Remember, it's a function of x prime. Okay, so this was delta x mu. So this formula becomes plus delta x mu of d mu phi. So, regarded as a function, how much has this function changed when you do this coordinate change? It's changed by this much. So the change in the function is given by delta x mu del mu of phi. Okay? So far so good, sort of obvious. Taylor expansion. Let us now understand how this works, let's say for a vector field. By the way, what is this object delta x mu? Delta x mu is a small change in a coordinate, and so is a prototypical upper index object. I think we call it contravariant. But for one index object, it's usually in mathematics just called a vector field. So this is an infinitesimal coordinate change is a prototypical vector field. It's a small little arrow at each point. How much you've changed your coordinate. Okay? So the change here is a vector field dotted with something. Whatever that something is called the Lie derivative acting on that object. Different people have different notation. Some people call it L mu. Okay? And in this case, this is like very fancy notation for something very simple. In this case, L mu is simply del mu when acting on a scalar field. Our job now is to determine what L mu is, the d derivative is, for more complicated fields, more complicated tensors than just a scalar field. Okay? And it's not a big deal because we know all the rules. Okay. So let's work it out one by one. Let's work it out for a lower index, let's work it out for an upper index. And then I'll stop the class. Okay. So let's see. Let's be careful. So suppose we wanted a mu of x. Suppose we wanted to see how a mu of x, it's an object with a lower index, changes, how a mu of x changes when you act on it with an infinitesimal coordinate transformation. Well, how does it change? We know the rules. We know that a mu of x is equal to a nu times del x prime nu by del x mu, except that a nu, and now we'll be careful, is a function of x prime, and this is a nu prime. Is this clear? Yeah, you're right. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. We'll just call this as a function. Thank you. X prime. We'll say this. Thank you. Thank you. Okay. So now what we want to do is to determine, what did we do here? Here we determined phi prime as a function of x prime. Yeah, so we determined phi prime as a function of x prime. So what we want to do is to determine a nu as a function of x prime and subtract that, a nu prime, from a mu as a function of x, subtract the functions. So we want to work this out now when it's infinitesimal, using this formula. Okay. So first, here, you see, what we have here is a mu of x plus delta x alpha del alpha a mu of x prime, sorry. X prime, delta x is a function of x prime. That clear? Okay? Same manipulation that we did here.
It is also delta
Delta
x prime.
x is a function of x prime. It's this thing. Okay? So a mu was a function of x. X was x prime plus delta x. Okay, and then we expand that to first order in derivatives. Now what remains is to work out this object. Everything else here is automatically, okay, this part is automatically a function of x prime. What remains is to work this guy out. Okay, now fine, let's work it out. Yeah, everything's very easy because it's first order. You see, we had x mu was equal to x prime mu plus delta x mu of x prime. However, to first order, that is the same thing as x prime mu is equal to x mu minus delta x mu of x. Because the difference between x and x prime involves delta, and that, when you expand it, is second order. Is this clear? Okay, so we can use that to determine this. Okay, so what do we get here? When we do this, we get one term that is delta nu mu. That's when we differentiate this object. And the second term we get is minus del, we wanted a nu here, delta x nu by del mu. Okay, let's use some less complicated notation for this. Let's call this, put a comma here. Means derivative with respect to its muth. Its muth argument. Is this clear? Okay. Now this is already first order, so whether here you regard this as a function of x or x prime, it doesn't matter. Might as well regard it as a function of x prime since we want everything to be a function of x prime. Okay. So what we have to do is to multiply this by a nu of x prime. Is this clear? Excellent. So now we have to gather terms. Okay, we gather terms and what do we find? On the left hand side we had del we have okay, and what now we have to find what we actually what did we actually want? We wanted the new guy minus the old guy. So we have a new mu of x prime plus delta x alpha del alpha a mu of x prime. That was the left hand side. And on the right hand side, what do we have? On the right hand side we have a prime. Now a prime, one term it contracts with is here, which just gives us a mu of x prime. The second thing it contracts with is here, but this is already first order. So in this first order thing, a prime and a are the same. Okay, so the second thing it contracts with is minus a nu of x prime delta x nu comma mu Is this clear? Now we want this minus this, so we subtract. So we get a prime mu of x prime minus a mu of x prime is equal to delta x alpha into del alpha a mu plus delta x nu mu a nu. Is this clear? Sorry.
There will be no brackets.
Sorry. Thank you. Okay. Okay. So the Lie derivative with the vector field x mu, the Lie derivative in the x mu direction is just delta x alpha d alpha, like for a scalar field, plus an additional term, okay, which involves delta x nu mu contracted with this. Okay, so delta x mu L mu, this, or maybe sometimes I can't remember the notation. Maybe it's called L mu in the delta x mu direction. We'll invent this notation. I'll change it to something standard next time. L in the Lie derivative in the direction delta x. Okay, this is equal to delta x mu del mu plus delta x nu mu a nu. Can you say that if you had many lower indices, can somebody guess the answer to many lower indices? Suppose I had 2 lower indices.
One for each of them.
Absolutely. It's clear that this is coming just from the transformation of the index. And the transformation happens index by index. Since we're doing infinitesimal coordinate changes, there's no mixing. So it's just one for each of these. So the general rule for many lower indices is a mu1 to mu n L delta x is equal to delta x mu del mu a mu1 to mu n plus delta x mu mu1 delta x mu mu1 a nu mu2 mu n plus delta x mu mu2 a mu1 nu mu2 mu n plus okay. Exercise. Work out the same rule for an upper index. Exercise. Show that, work out the action of the Lie derivative delta x mu on the metric. And show that up to some plus minus sign that this is given by delta alpha delta x beta plus delta beta. Do you understand what the statement means? What you do is to check how the metric transforms under a little coordinate change. Metric is just an object with two lower indices. We use this formula that we have. You get some answer. But you see, this answer involves derivatives of now not just any old object, but derivatives of the metric. Now, derivatives of the metric are special. We know that every derivative of the metric can be written in terms of gammas. So by manipulating, show that the formula for the change of the Lie derivative in the direction delta x mu of g alpha beta is proportional to, I can't remember the proportionality factor, may even be 1, del alpha delta x beta plus del beta delta x alpha, where delta x beta has been lowered now using the metric. Okay. Let's stop today's class here. In the next class, we will discuss curvatures.